Alright, now, so we're going into our third and final video, at least of this portion of the content. We're going to turn our sights from our galvanic cells, which happened on their own spontaneously, to where we're looking at electrolysis. Now, if we're breaking down that term, electrolysis, we're looking at electrolysis, the breaking down, lysis, which means breaking down of things using electricity. Now, when we have electrolysis happen, this is where we're actually forcing current through a cell to produce a particular chemical change. And that cell potential for that is going to be negative. To give you an idea, if we're looking at, and this is what we're going to use in a second just to do an example, this is our process that we're going to use to figure out how much current or how much of a change is going to occur over that specified amount of time. We're going to start off with our current and time information, then moving on to the quantity of charge in coulombs, which will lead us to the moles of electrons, moles of the actual copper, or whatever the case is what we're using, out into grams. To give you an idea of something that you want to make sure you note down, when we deal with amps, we're going to deal with it in terms of coulombs per second, okay? So if we have current and time, quantity of time, we're actually going to end up with the coulombs per second times seconds. This will allow us to get rid of seconds, and we'll be left with just the quantity of charge. From that, we move into the moles of electrons. And of course, we see the relationship here. To get moles of electrons from that, we're going to have the coulomb of charge times 1 mole of electrons over 96,485 coulombs. We've seen this conversion factor before. We talked about it a little bit earlier when we talked about delta G naught. Okay? Now, if we're looking at this example, because I believe this is one that you really have to do it in order to get into it and to understand what's going on. So, we're given a couple pieces of information. We have this unknown metal M that's electrolyzed. It says it took 52.8 seconds at 2 amps to plate out 0.0719 grams of the metal. And we're looking at something as M nitrate with 3 nitrates attached to it. So let's use some basic information. We have 52.8 seconds and 2 amps. If you remember talking about this before, we said that that's going to give us, we'll start off with our time, 52.8 seconds. Set up my table. I know some of you love this table so much. And we said that amps is really just coulombs per second. So that means 2 coulombs per 1 second. This allows me to cancel out my seconds here and to proceed. Now, the next conversion factor that I'm going to need is I'm going to actually need my number of coulombs per moles of electrons. So let's take a look. Well, 1 mole of electrons gives us 96,485 coulombs per 1 mole of electrons. Okay? Now, taking a look at this, when this is electrolyzed, it says we go from the metal to this form of it. That means that we had to lose 3 electrons. So that means 3 moles of electrons to 1 mole of M. Again, because of the fact that we're going to this form of M, lets us know that that's where those 3 electrons are coming from. And last but not least, actually that'll give us our moles of M. So taking it, plugging it into my calculator, and I got 3.65 times 10 to the negative 4 moles of M. Now, that's giving us how many moles that we actually utilized here. If we look at it, it told us that we used, in that time, we plated out 0.0719 grams. Well, if I have the number of grams and I have the number of moles, I can figure out what the molar mass is going to be. So, just plugging it in, I'm going to do 3.0719 grams over 3.65 times 10 to the negative 4 moles. In the end, I know I'll be right because I have grams per mole. And when I go ahead and divide these, I'm going to get 197 grams per mole. Using my periodic table, I find that the mass that's closest to this is going to be gold. Gold is my actual metal in this case. Okay. Now, when using this in terms of an overall commercial method, we're going to see that we use electrolysis or electrolytic cells in many different situations. Producing aluminum. If I remember when I was growing up, there are a lot of people who always wanted things chrome plated. All these different things, to silver plating, all those types of things that used to be used widespread, and that was sort of a status symbol, if it were. There are a lot of materials that are used and prepared like this, like when we purify certain types of metals. Also, when we do the electrolysis of sodium chloride. These are all ways that we currently use the electrolytic process. Just giving you an idea. If we're producing aluminum in this case, so notice that this is our external power source, and we're using graphite. Why graphite? Graphite is inert, so it doesn't react with the solution on its own. Okay. Now, in here we have our carbon dioxide, which is going to be formed at our anode. And this is our mixture of aluminum oxide and this complex ion with sodium, aluminum, and fluorine. As this reaction takes place, the aluminum sort of falls out or filters out into this tank, and we can actually extract it in a molten form. Okay. Same thing happening because we have our power source. We're booting out electrons this way, which means that we're going to be pulling from this way, plating this spoon with silver. And same thing, the down cell for electrolysis of molten sodium chloride, helping us to produce more sodium chloride. And also at the same time, we're having a production of chlorine gas, which we can actually use for other things later on down the road. Now, for electrolysis, the big thing that we're going to need to do is we're going to need to be able to calculate how much is coming off from those cells, and actually being able to predict a few things about the signs of like our delta G values and so forth. But remember, electrolysis is not spontaneous. Since it's non-spontaneous, delta G will be positive. Our cell potential will be negative, but our delta G would be positive because of the fact that we actually have to put in energy in order for it to happen. All right. That being said, this is where we're going to end it for now. I will see you all in class to answer, I know, the many questions that will come up from this. Have a great day and see you later.